All right. Well, welcome. This is going to be a very intimate talk. There's not a lot of people, so I have a lot of slides, not a lot of text, so hopefully that's not very boring. But since we're not that many people, I'm perfectly happy in making it much more interactive, and interrupt me whenever you think that there's an interesting question to ask. Okay? So the idea of this talk is basically to talk about distributed systems, distributed databases, and show how we went through the reasoning behind how we put together our distributed database system to support this distributed, globally distributed architecture. So what I'm going to do is talk about the analysis of data that we did. And I think that at this point, you'll see that a lot of the types of data that we have, they probably will apply to your own applications too. So you kind of have the relationship there that you can leverage. And then I'm going to go in detail about how we put together the different systems based on this data taxonomy and types of data, and if it's highly available, if it's not highly available, if it needs to be, it can be shardable or not. So I'm going to go piece by piece, explaining what the architecture is. So I guess it's, I want to make sure that this is not really about our systems architecture. Obviously, it almost looks like our systems architecture, but it's really honing from a database perspective. So I'm going to pick a few systems to showcase the different types of data semantics that we have. Okay? I don't know if I have to go through this. So how many of you have used NoSQL or in general, Cassandra or otherwise? All right, so not that many. Okay, so maybe I have to go through this slide. Okay, so kind of a bit of a spoiler alert. We have everything is all of our systems either use MySQL as our relational database or Cassandra as our NoSQL database. We also use S3 for backups and archiving, but that's more of a boring part of the data. And there's basically three reasons that influence if we use one or the other. Obviously, we need transactionality. MySQL is the way to go, right? Very strong ACID semantics. Cassandra, there's something there, right? Obviously, it's durable, has some no atomicity. There's some isolation, but it's not a relational database, right? Now, on the other end, when we need availability, Cassandra is the way to go, right? MySQL is really not very available. I mean, you can do all kinds of replication. You can promote failures really quickly, but it's not highly available as Cassandra is, right? Cassandra is a distributed system, masterless. You can have a huge amount of replication. You can actually even work across data centers to have complete copies of the data that are in sync. So that's where it really shines. And then there's another part that is also interesting when you design the data store is that what's the queryability that you need from that data store, if that was even a word, right? Do you need to do complex queries? Do you know in advance what queries you need to do? If you don't, then MySQL is going to provide you with much more flexibility over time, because maybe 2 months from now you see that you need to access the data store from a very different perspective, and just adding the certain indices it will allow you to do so. With Cassandra or NoSQL in general, you usually have to have a little better knowledge of how you're going to query this data, and it's going to be more difficult for you to add indices or denormalize data so that it's fast. So those are the three things that kind of come across when you have to decide what kind of data store you want to put in. So I'm going to start with a taxonomy. I'm going to go very fast here because I don't think it's too necessary to get into the details, but this is an example of the main types of objects or the main types of data that we have. And I think that this will correspond to many of the things that you may have in your own company. So obviously one of the things that everybody will have is global objects, things that are common to every tenant. In our case, the tenancy model is an account. Every account has its own thing. Maybe you guys have users. Maybe you guys have another type of tenancy. Things like plans, settings, everybody sees the same thing, right? If you used our multi-cloud marketplace, the library, you can also think of that. Those are global objects. Everybody browses those things, and they can import them into their account. Now, the other part that I have here is the dashboard objects. That's basically a way to say everything that you usually see in your account. All your server configurations, the templates, the inputs, all this is visible to your account only. That's basically the main object that you use every day, through the dashboard or through the API. And then you have things like, we have things like polling, cloud polling data. We need to poll the clouds for changes and then reflect those changes into your account, right? Those are things that are more sort of appear in your account because of whatever cloud you have connected to has some changes. We need routing data because we need to know where instances are. You may run your infrastructure across many different clouds. We need to know where your instances are and how to make them talk to each other. And finally, the boring data of monitoring and syslog. You just basically write once type of data, like big data, but not very interesting. Now, with all these things, we can slice this taxonomy in two different ways. Number one is based on who uses the data. So if we partition these depending on who uses the data, we're going to have, if this works, that you'll see that basically all of this part of the data, the global data and the assets that you have in your account, that's what the users usually interact with. The users, that's what they see. However, this data down here, this is data that really the instances or the cloud needs to utilize, right? When an instance comes up and starts sending monitoring data, well, that's the client of the monitoring data, right? There's another way. So from this perspective, what we can do is say all this data that is on the top, let's try to put it very close to the user. So when they access it, it's as fast as possible. This data on the bottom, let's try to put it close to where the instances are because that's where the interaction is most important. But there's another way to slice this data. And that's not because of who uses the data, but how many data do we need to have available. And that's basically, I guess it's obvious in a sense. It's like some data needs to be available to everybody, the global data, and the rest of the data is really only about your account, right? Nobody but you who needs to have access to your tags or your servers, right? So there's another way to split that. So if you superimpose these two different, that will allow us to know how much data that we need to keep together. If we superimpose these two divisions, you see that you end up with three quadrants, if you will. Some global data that needs to be close to the user. Some data that needs to be close to the user, but it's really only available to your account, so you don't have to have this globality for all users. And then some data that needs to be close to the instances of the cloud, and but is also for your account. Okay? There's not a fourth quadrant here, which would be global data that needs to be close to the instances, because it doesn't quite make sense. Although, in a sense, you can think of routing data as being something similar. Routing data, it has to be global enough because you need to know where the instances are, but it's really only for your account, right? Nobody messes with your instances other than you. Okay, so I'm going to use these three classifications to show how we build our databases. So I'm going to divide this thing in 4 quadrants. I'm going to start with the first one, which is the easy one. Data that needs to be close to the users, but it's global. For this type of data, we basically use MySQL databases because most of what's there is very relational. New plans. You have users that have passwords. You have plans that have settings. It's a small piece of data in a sense, but it's very transactional. Okay? So we have masters and slaves and the whole shebang there. That's representing a big system that I call it global. And that's basically how it's built. Now, probably, if somebody's paying attention, you probably are thinking, well, you're telling me that this is a global data that everybody needs, and you're putting it in MySQL, which I told you that has the less availability than Cassandra, right? So here's what happens. We need this to be transactional, and the availability of this data needs to be basically for read purposes. Everybody needs to be able to, at all times, log in, use the settings, access their plans and stuff. But we care less about you being able to create a new setting or to add a new plan. So for that, what we are doing is we have this massive custom replication of all this data in a read-only fashion in the other systems so that all of them are highly available in terms of read. Even if this goes down, the rest of the system continues to work. We cannot add users. We cannot add plans. But the rest of the system continues to work. right? So the availability, we've basically changed writes and read availability so that we can take advantage of the transactionality of MySQL, but at the same time, we have high replication. Why custom replication? For several reasons. We cannot use the normal MySQL replication because the systems on the other end, which I'll explain next, those slaves draw from multiple masters, and MySQL doesn't support that. That's one reason. The other reason is that we need to do some transformations on some of the columns, so that's nice to be able to do it that from a custom perspective. And also, if the stream of replication breaks, you need to have a good way to resync the data, because you don't know where you left off, basically. Okay? So that's that. So that's the easy one. The next one is data that needs to be close to users. That's what they usually utilize in the dashboard. But it's really, it's basically shardable, right? You need to have the whole data for your account, and I will never access the data in your account and the data on another account, right? So I have 4 different services representing here. The first one is what I call the dashboard, which is mostly what you used to use in the dashboard. Like, it's very transactional. Servers have settings. Deployments have servers. Servers have server templates. Server templates have scripts. The typical things that you're used to using in the dashboard. All of this is based on MySQL databases. Okay? Huge replication, lots of slaves for parallelism and all these things, but it's really MySQL. An interesting thing from this MySQL databases is that every single row that we have in the database is tagged with the account ID. So at any point in time, I go to any table, I can know exactly if this row, what account this row belongs to. And you'll see that this is important for sharding. Okay? Another example of service is tags. Well, yes, it's tags. So tags, for example, is something that is much simpler from a data model perspective. It's just saying this object has these tags, or I can do the opposite. Given this tag, what objects have this tag, right? So there's not a whole lot of more things that you can do with that. So that maps much better with something like Cassandra. Okay? So obviously that gives us great scalability from that perspective, especially writes. And actually that's one of the things of the audits there. The audit service is the service that allows you to basically save audits. Like anything that happens in your account, you have an audit entry, is going to be stored in these systems. One of the best things that Cassandra has is the write scalability. In fact, writes are much faster than reads, right? Because of the SS table scenario. So this is a perfect fit for that. Now, we don't want to have terabytes and terabytes necessarily in these Cassandra systems, because most of these audits are never going to be used. I usually don't go and look at an audit entry for a year ago, right? So we prune that to keep it smaller in the online database, and we archive it to S3. If you still click, you will go and get it from S3, but we don't have to have a massive amount of data. And then the last one we have here is the event system, the user notifications kind of thing. And that, I put it here because it's another interesting example of using Cassandra, and that is using TTLs. Anything that you put in Cassandra, you could potentially put it with a TTL. So if you put a row in the database with a TTL of 10 minutes, after 10 minutes you query and that won't be there. And that's exactly how we do this evented system, that we can, for everything that you do in your account, we can generate a user notification with a TTL of 10 minutes, so that at any point in time, if I query for all your recent notifications, I'm going to get everything that is there. Everything that was more than 10 minutes is going to be automatically deleted. It's kind of a weird way to use it, but it works well because you don't have to do a lot of client filtering or things like that. So in this quadrant, we said that we only need to have data that belongs to an account. So that obviously means that we could potentially have these systems and replicate them across. And that's what we call clusters. So it's a typical sharding, I guess, practice, right? So what does this really mean? See if I blow up a little bit. That really means that we can have the same exact systems on the top, but we apply different data to them. So That way I can have a set of accounts that need, that, for example, what is that, US East? A set of accounts that are on the East Coast, and I'm going to map them into a given cluster 1 East Coast cluster, right? Everybody that has accesses the dashboard in the cluster 1 is going to have fast access from the US East. Now, I can also move accounts from cluster to cluster, right? So doing this, we have pretty good horizontal scalability because these things are completely separate from each other. They don't depend on each other. I can do also things like independently scale my US East cluster. For example, there's a lot of customers in the US East. I can have this cluster, the number of servers for this cluster can be much bigger than the number of servers in Japan or in South Asia, for example. Right? I can also do things like I can deploy different versions of different clusters. Maybe there's a beta cluster, right, that I have some guinea pig customers on. Or I can provide different services in different clusters too. I don't have to run the same code, right? So by horizontally scaling in clusters, we can achieve pretty good scalability.
Question for you.
Yeah.
Can you guarantee that specific data element stays on a specific cluster? For example, Japanese data stays in Japan?
It's at the account level. Whatever you put that account is going to stay there. Yes. Yeah. Yeah. All this migration is completely manual. Your account is not going to be magically migrated to Russia if we had a cloud there, right? You can say now maybe my majority of my clients for this account are going to be in, I don't know, in Australia because my development team moved there. Well, we can move it there because you requested so, right? Okay, so I guess the same way that we can do this for account data, we can probably do the same thing for the instance data. And actually, that's what we do. But instead of calling it clusters, we call them islands. So what's the difference here? The difference is that we said that in this lower quadrant, we want to put this data close to the cloud, not close to the users. So this is data related to the running things, not the users wanting to run things. Okay? So I have a pseudo illustration here to see if this to make this clear. So for every island, I have 3 different services, example services. Okay? So the little green dots depict the instances that you may be having in the cloud running, that they will have to access these services, right? So the idea is that if this is a cloud, and you have some instances running, we want to deploy our services really close to them, right? Because if somebody starts sending monitoring data, well, they send it next door, right? And so it's collocated where your instances are. So now, have in mind that what happens here is that you as a user, you may have instances running in all the cloud infrastructures that we have, right? So the relationship with your instances here or where your cluster is completely orthogonal, right?
So that means the cloud one is the Google Compute Cloud. So that means the RightScale services will be running within Google Compute Cloud?
Absolutely, yeah, absolutely.
And it holds true for private cloud also?
For what?
For a private cloud? Let's say if you...
Yes, well, so it could, right? So we could decide where to deploy these islands.
Can you repeat the questions that were asked for the camera?
Yes. So, the first comment was that, does this mean that our infrastructure, for example, if this cloud one was GCE, cluster compute, does it mean that we will have some of our infrastructure running there? Yes. And does this apply to private clouds? It could. We can decide where to deploy infrastructure so that it's close to where your instances are. But that doesn't mean that we need to have infrastructure for every single cloud. We just want to have infrastructure and it's not really geography, but pseudo-geography, so that at least the instances that are close to that geography are calling home in a very, next door kind of thing. But we don't have to have this absolutely for every single cloud. So for example, you could have an island in US East that serves, obviously, Amazon US East and Rackspace Dallas and some other clouds that are somehow close to that one, right? It's not a one-to-one thing. But we can decide how many islands we want and where to put them so that we kind of cover the networking space. Does that answer your question?
Yeah, that answers. So, I mean, it was more specifically in terms of, let's say, that pink arrow, right? If there was a outage in the network, let's say.
Yes. No.
And
Outages in the network are coming soon. You'll
right.
see.
So
Well, I'll see. I have a couple slides. Maybe
yeah.
that.
Yeah. So that's.
If when I talk about this doesn't answer your question, then, well, let's Okay. So let me explain how we build the database systems here, and then we'll get into the failure modes. So what we use here is a combination of MySQL, Cassandra, and really flat files. And I've picked these three systems because they're really different, right? So one of the one that I have in the polling, that is just some systems that continuously poll the cloud for changes, and they store the state, and they can compute the differences. They basically see what's happening, see what happened before, and generate the stream of events, of changes. And they send these events back to our main systems on the account level stuff. Okay? That is right now using MySQL with a master-slave replication and the whole shebang. But the data model is not very difficult. So it wouldn't be difficult to port this to, say, Cassandra if we wanted to. We don't really do joins. Basically, it's as simple as saying, oh, I'm going to pull instances for this account. What are the instances? Here. What are the instances that I have in my database for this guy? What is the diff? I'm storing the differences, and if there's any event that I have to send back, I'm going to send the event. There's no really joins and funny stuff. So that could be ported easily to something that scales better. But the interesting thing is that for every of these systems that we have, we can horizontally scale them as much as we want, because you can have systems that simply pull a few accounts. So you could really scale that in a very easy way. So that's why we haven't had the urge to stop using MySQL for this. It's quite convenient. Another one that is kind of interesting is our monitoring system. Right now, it's based on, it's a collective system that gets all these monitoring metrics and really stores them in RRDs, which really ends up being flat files. That's weird. I mean, it's not necessary to have something too complicated to achieve that. Obviously, then we have the problem of to back it up and replication and stuff like that. But that's a very simple system. We're going to replace that soon with a Cassandra-based system. But this is an example to say about not everything has to be uber complex. Okay? And the last one, which is the most interesting, is the routing systems. And the routing systems use Cassandra, but use Cassandra in an interesting way. And that's why this dotted line goes across islands. So in Cassandra, you have a logical ring of data. And you can tell Cassandra that you have several data centers, meaning several separate physical places that you want to store data, and how many nodes you want on each of these data centers. And Cassandra, on its own, will make sure that every single data center has a full copy of the data. But when I'm in data center 1, in island 1, and I do a read, it's going to be a local read. Okay? So if I'm in island 2, if I read the same data, it's going to be a local read in the same way. And the writes are local, and then they're replicated, eventually consistent across. So that's a very powerful feature of Cassandra, which is really important for this global routing infrastructure, because we need to be able to locate at any point in time where every single instance of your account is, because when you do tag queries and send messages from instances to instances, that's how we use it. Kind of a routing table that has all the information about the assets.
Using Cassandra, can you tag certain data that you say, I don't want this particular data to move from this data center?
No, you can't.
I want it to replicate, but not, replicate for HA capabilities, but not necessarily read, for instance.
Well, so let me explain a little better how this works, because so you cannot control this piece of data cannot make it into that cluster. Like, if, say for example, in island 2, maybe that's a country that has some special thing, and you say, oh no, I don't want any of my data going there. You cannot do that. That's what I thought you wanted to ask at the beginning. But what you can control is within each data center how many replicas you want, regardless of how many replicas you may have in the other data centers. So for example, the way we run this is for our specific settings, we have 3 replicas of every single piece of data in a data center. And then there's 3 replicas there and 3 replicas on every single data center. So that's the control that you have. So it's replica times data centers. That's really the amount of times that you will have that data written somewhere. Yeah, you cannot control those things, which are interesting, and maybe someday you can do it, but right now you can't. Okay. So that's basically what I talked about. Okay. Now, let me go to the next slide. So now let's take a look at where we are. So we looked at the global system there. That was something that I was replicating, custom replicating into every single cluster on top. So it's like a stream of replication data that goes to every single cluster. And we have resyncing capabilities. And because of the scalability of the clusters, we can spread across different geographies based on where the users need to access this data, right? And we have a way to move users from cluster to cluster if they so want to change it. In the bottom, right, we do the same thing close to the cloud. So while that I just put geographic things like the east of the US or Japan, in here really it's about the cloud, the actual cloud that they will be running on, right? So now failure modes, for example. Now if I have something running on AWS East, this island 2. If island 2 is in AWS East and the whole AWS East goes down, right? What happens with the instances that I was managing? Nothing. They're gone. The whole cloud is gone, right? Our instances and you guys' instances. So it's kind of an interesting failure scenario. There's nothing to manage. We even lost our servers if the whole region went down. I'm talking about, it never has happened. There's only been glitches region-wide, but it's never really gone down.
You do have a copy of it in your, I mean, you know that which instances went down, right? Or you know that?
Yeah, we know which instances went down, but they went down.
They went down, yeah.
So this is the instances so the services that we have collocated with the instances is to manage the instances. So if the instances are not there, you cannot really manage them. See what I mean? You would be able to, from your cluster, start launching elsewhere, right? You may shift your load into whatever, Azure.
Do we lose this data also, or does this get replicated?
There's replicated data, but there's a lot of this that you don't care. Sorry, the question stuff. Yeah. There is every data that is in here. There's a backup. Okay, but think that a lot of these things, they don't need to even be replicated. The routing will automatically be recreated if the whole region went down and then it went back up. Because of Cassandra, you will end up having all the data there because you have the full replicas elsewhere, right? For the polling data, we really don't even have a backup. We don't need a backup because you will immediately discover everything as soon as you start polling again. I guess that the first iterations will be slightly slower, right? Because you'll generate a lot of events, but we don't need to. We have backups that we could warm up so you don't have to generate more events than necessary. And then the monitoring data, we have it backed up in S3.
Right. Sorry for asking so many questions, but what I'm really concerned about is, let's say in this data representation, I don't see a representation of jobs or tasks or what you call as write scripts.
No, because they're not here. Those things are not there. They're in your account here in the cluster, in your cluster.
And what about I think I asked this question before also, but let's say I'm running a script to upgrade my servers, to take an example, right? And I have 10 servers to upgrade, right? Now, that script must be running in one of the instances in my, let's say AWS East, right?
Yes.
So your server will be executing that script in AWS East to upgrade my servers in AWS East.
Yes and no. So the server will be executing in your instance. The server will have contacted your cluster and say, I need to do this. Tell me what to do. It's going to get the script and it's going to execute it.
Yes. So now what happens? What happens if a RightScale servers, which is executing this step one, which is upgrading these servers, and after upgrading third server, it goes down?
So let let me say it again. So the running of the script is going to be done by your instance. So the green guy here, not this blue infrastructure that is ours. If it helps, yeah. Right? So the script, so this guy will be connected through the routing to your core. And he'll download the script and everything that he needs to do. And then once he has it, he starts executing. If this thing goes down, he will stop executing. But the automation is based on your cluster. This is not going to provide automation.
The agent talks directly to
Yes.
the accounts out there. The agent running inside the instance talks to RightScale.
Right.
No. So I mean, in the RightScale dashboard, I have a way where, let's say I have an array, and I say, okay, run this script on this array. Right?
Yes.
Now,
We will contact, so let me tell you the sequence of things that happens when
Yeah.
you do that. You go to your dashboard, and that's this guy providing the dashboard, right? You do run script in array, right? These systems will figure out which are the instances that belong to that array. It will send a message to all of them through this global routing. Maybe one instance is running in this island, maybe one is running in that island, maybe one in that island. All of them get a message, say, do this. These guys are not involved. These continue polling, these monitor stuff, and this just is the routing infrastructure. Once you have the message into these instances, they will, that are your instances, they will be the ones running the script. So if something fails, we will know here.
Okay.
See what I mean? It's the main process is here. The brain is there.
Okay, so the brain knows that out of we instructed 10 instances to run the script, but out of that 10, 5 responded, but 5 did not respond.
Right, or failed in the middle, exactly.
Or failed in
Yes.
the middle. Oh, I get
Yeah,
it
these
now.
systems are helping with other tasks, basically. They're not the runtime thing that you're thinking about, running scripts. They will help in getting these instances send the data. They're monitoring data very close by, for example. That's the only thing that this does. This will pull the cloud, that's easy, and then this will just allow these instances to send things out and receive things in.
Yeah, but then there's still a master who's sending these jobs,
Yes.
right?
Mm-hmm. Correct.
What about the HA of that one, right? I mean, so I'm really concerned about the state. What happens if the
Yes.
state is lost, right? Because if I don't have the state, that what went through and because
Okay, so if this fails, so I'm going to go with the failure on top. If this fails, basically you're losing what you want to manage. Therefore, there's not much you can do until that comes back up. You cannot continue. You cannot manage more instances over there. Now, what you're saying is that what if this fails?
yeah.
Right? Because this is where the main brain power is, right? So if this fails, you would be screwed. If the whole region where your cluster is fails, you will be screwed. Except that we have a DR strategy. So the DR strategy is basically pairing two clusters. It's a well-known pairing, right? Cluster 1 and cluster 3 will be paired. And you know that because we pair them, we're going to replicate all the data that we have from one to another, both from the MySQL perspective and from the Cassandra perspective. So if the whole cluster 1 region goes down, we would have a way to get this back up so it serves your account. And I'll get into the details with that, right? So there would be a hiccup if the whole thing goes down. You won't be able to maybe log into your account for a few minutes. But we'll get you back up fast. Wait, the microphone.
I think he is more concerned about the state, right? So if there is a problem with the brain, quote unquote, right, and I've executed this across 20 instances in an array, he wants to know, out of all of those instances, which was the last instance that received or completed the script or task at hand versus which ones are stranded.
You
quote
will know
unquote.
because of the audit entries, right? Everything that you do as a script, it will generate an audit entry. So if 5 out of 10 fail, you'll have 5. The audit entries for those 5 scripts will tell you this failed. So and the state is here, right, in the audits. So it'll be up there.
Yeah.
And we've seen that in real life, right? If I've had things do exactly that, unfortunately, I have to now manually look at all the execution to make sure there hasn't
Right.
been any error within any of the instances in the array, right?
Let's say we upgrade our servers two times in a day, right? And we cannot afford to go and look at manually. Basically, we need a process such that process resumes itself. So when I said upgrade or run a script on this array, no matter what, it should complete, right? It should complete in the sense we need, even if the server who was executing or the brains who was executing this, it failed, it has to save the state somewhere, so such that if it fails, another server comes up, it knows, okay, I have run the script on 5 servers, 5 are remaining, let me continue from there.
Right. So there's different ways of trying to do that easier for you, and one is using tags. If your script, when it completes, sets himself a tag, the server sets himself a tag, say this is the SHA or the version or whatever you're trying to update, that could tell you very easily which ones are in which version. We use that all the time. When we update code in our systems, we have one tag that says what is the SHA for the repo. And you can see, okay, which ones are the ones that are in the right thing. So until it finished, you don't write the tag, so then you know if something finished or not successfully. But that's kind of outside this, right? I mean, and there's things that we could do to help you with this, so it's important to know, right? We might put something that makes it even easier for you to track these things. But the only direct state that you have is the audit entry of the script, right? You could use tags to help you with that, but really, at the low level, audit entry is the only thing that told you, yep, that didn't quite work. Now, mind you that this losing a region does not happen often. In fact, it's never really happened. I'm just talking about if that happened, well, it's much more important to take care of it here than here. Because you cannot manage the instances anyway, so you lost it. That instance is lost forever, right? Even if the cloud comes back up in an hour. So what happens here is basically that we're going to use master-slave replication, MySQL, the typical stuff for every single database that we have across. And then we're going to use the multi-data center replication of Cassandra to make that copy. So that will be free, in a sense that we can say, this ring here is associated with this other ring there, so connect them as 2 data centers. That means that everything that I write locally here, I know there's going to be a copy over there, and vice versa. So it's an easy way to keep 2 full sets of data in sync. Cassandra does that for us. Obviously, everything that we write here, it will never be read from this other guy, because we said they're different sets. The accounts that are here, they're different than there. But in the case that we have to fail over to that one, then, okay, the data is already there. Now you can start serving it. And one of the things that we do, that we have planned on doing is, instead of basically flipping everything from, the whole cluster goes down, instead of flipping it to the traffic to cluster 3 directly, we, instead of starting to replicate the infrastructure and launching however many servers we have here in cluster 3, what we do is going to shift the load, start adding more, enabling more accounts. This is terrible. There you go. Enabling more and more accounts to be served by this other cluster so that we get to the point that everybody is served. But if we pretend to have a full request tens or hundreds of servers, new servers over here when the whole cloud went down, we're probably not going to get them because everybody will try to do the same thing, right? So instead of doing that, we have a system that can allow cluster 3 to start serving some of the accounts that he already has there replicated.
I'm not talking about that worst case. I'm not talking about the entire US is going down. What I'm talking about is instances going down. Since your infrastructure is also running on Amazon, right? Virtual machines. Those virtual machines can go down.
Our virtual machines?
Yes.
Yes. This is about Datastore. I mean, I can get into all of the details that you want for that. So if you're talking about when we lose instances, that's a different story. Yes.
Yes. I'm not talking about the entire US East going out.
Yeah.
So
yeah.
It's
No, our instances, these services, they're replicated across all the availability zones. We have, depending on the service, has more or less availability, in terms of availability zones failing.
So very simple question. So let's say if I trigger a task saying run this script on this array, right?
Yes.
And that array is 10 servers long, right?
Now there will be a VM which will be executing this task of dashboard maybe.
No, there won't be. There will be a message sent to the instance that has to do it, your instance.
Yeah.
There'll be a record somewhere that says, yes, I need to tell this guy to execute foo. But that's just data, it's not process.
But somebody generates that message, right?
Yes.
So the whatever machine is generating that message or tracking that message, it's a distributed task, right?
No, it's a message. It's a write to a data store that somebody picks up and executes later.
Somebody has to generate that message, right? No, I mean the message has to be generated also, right? So it has to be coordinated, right? It's a coordination service, right?
It's writing something to a queue, so to speak.
It's writing something
Right.
to a queue, right? And you wrote 5 entries and you failed, while you had to write 10 entries.
No, you write the 10 entries, and then you say, is it in progress or not? So if you want to execute
offline, yeah.
if you want to execute 10 things, we're going to put 10 things in a queue or a database, right? That either succeeds or fails, transactional. When that's going to actually execute in your box is going to be later. But you have the list of the things that you need to do written in many places. And then somebody will end up picking this and making it happen. So it's different.
Okay.
See what I mean? Well, we can take it offline. I don't want to. But, so basically, there is no particular process that is going to be in charge of doing that little thing in our services. Somebody will pick it up. But there's no process that if it fails, then that task is not going to happen because it's in the database. Right? Somebody will pick it at some point and make it happen. And we have systems that can time out and they can check things that have not been picked up in enough time. And then at some point you say, well, this has not happened in whatever, 5 minutes. Audit entry saying this failed. Right?
If from my little understanding of this, but I think what he's getting at is if he says to execute the scripts in the array, those array write to some couch-based location, or if you will, right? What he's concerned about is that couch-based location, right?
Okay, so that would be, in this case, for scripts execution, this will be initially put in a MySQL database. We'll have 10 tasks to be done in a MySQL database. And then we have some systems, distributed systems, that check what needs to be done and make it happen.
So at certain intervals, I've had it where I've said I've told it to execute a lot of scripts, for instance, and I received couch-based error messages. I know that those tasks didn't get written to a particular queue or what have you, well, right? And hence, they never got down to the instance because the instance went up and said, is it there? It's not there, so the instance didn't do it.
Yeah.
Right? It's the agent inside the instance that says, do I have something to do? Not, hey, you have something to do, but do I have something to do?
Yeah, it's more from the design fundamentals. It's like coordination services, right? So, I mean, it has got to do with, I don't know how you have implemented, but there are ways, it has to do with leader election, right?
No.
It has to do with distributed, I mean, you have to have it, if you're doing a set of tasks, basically, right? It's a coordination, if I have said task 1, task 2, task 3, right? It has to be done in exactly those lock steps. I don't write into a database and then somebody picks it up, right?
That's what you do. That's exactly what you do. And that's your coordination. That's your coordination.
You write it to the database and the agent picks it up.
Yes.
What if you write into the database fails or
No, then it's transactional. That's why it's in MySQL. If you say if you click in the dashboard, if you're going to do the dashboard and you click do this, we'll tell you yes, I'm taking note of what you want to do, or it failed. And then this will happen asynchronously, right? It will happen maybe 5 seconds later, but I have written down what you want to do, and I have systems that will make sure that either happens or times out. You see what I mean? So we're using the MySQL, in this particular case, we're using the MySQL mutexing, or like the transactionality, to basically make sure that we have written down what you need to do, either that or fails.
if MySQL master fails, then you have a disaster.
Then you have, yes, if it's MySQL, you have the slave, right? And the typical thing. Yeah. If it's Cassandra, then it's different. But we cannot do the synchronicity with Cassandra because it doesn't have locking. You could use Zookeeper and something on top to do this coordination, but Cassandra itself doesn't have transactions, right?
You can use the zookeeper itself to store that task.
You could, but it's the same thing as storing in a MySQL. It has less availability, but it's the same thing. Availability is not, you're not losing data, right? So
you don't use zookeeper to store that because zookeeper is highly available.
it's more available.
Yeah, it's available, more available than MySQL, right?
Yes.
And it is solid. I mean, it's solid, it's
Sure, MySQL is solid.
MySQL is solid, but not. I mean,
It's not highly available, but you won't lose data, right? So MySQL is as, yeah, I think we have to wrap up. MySQL is as durable as Zookeeper, right? You won't lose data, but you may not have it available, which is a different thing. If you're worried about losing data, MySQL is not going to be worse than Zookeeper, right? So you may not be able to do it at that point, but the data is there, replicated somewhere.
more about availability.
Right. Let me finish this, and maybe we can take this offline. So actually, I'm sort of done, I think. I don't know if this was clear what happens here. Basically, everything is replicated only in one other place, and then we can gradually enable more accounts to be served so that then all these new servers don't get immediately overloaded if we say, now we're going to serve double the accounts with the same infrastructure. There you go. Conclusions. I don't know. It's been a bit difficult to describe some of these without going into too much detail, but at the same time leaving things out. But hopefully, what I wanted to show is that we use a combination of relational and non-relational databases, kind of depending on the system. And we've gone from one to another and gone back too, right? It's like, it depends. Some things are good, nothing is perfect, right? And also, that I think that the gist of how we distribute the data is, I hope that went across, that we cluster, we partition based on accounts, so we can put these pieces of data very close to the users that need it. And we do the same thing in putting the pieces of data close to the clouds. Because when the instances need the data, let's put it close to the instance. When the user needs the data, let's put it close to the user. And the size and number of these islands and clusters, we decide. We can put more clusters, less clusters, and more islands or less islands, depending on how much coverage we want to get. And that's it. And the DR strategy is something that we've actually never used, but we have everything replicated both ways, so we have a way to start enabling accounts on the second cluster. And that is it. And I don't know that there's much time for questions.
If we have any questions, apart from we're going to take offline, any other questions? We got one over here.